Okay, we're here again, day 21. That's a lot of days of calculus. And in fact, not very many of those are calculus, but we're now getting into it, which is kind of why we're here. This is a Calc 1 course, and we want to dive right on into it. And section 2.8 in the text gets right on into it. So it takes what we have at this point, which is a definition of a derivative at a certain point, which is this. So if we want to know the slope of the tangent at a certain x value, let's say at x equals a, that's kind of where we left off in section 2.7. Now we want to take issue with that same process and say, yeah, but I don't want to calculate the slope of the tangent at a certain x value. I want to know what the derivative is at any x value. So we want a function. We want an answer that's a function of x that we can throw in different x values. So you'll see the similarities here. We want a function which is defined in terms of the original variable x, only it's a new function. It's called the derivative function. And what is it in terms of these same x values that we plotted on the original function? So if it looks very familiar to what we developed in mid-chapter 2 here, it is, except now it's not a number for an answer, it's a function. So we can have a function of x, which we'll do 3 examples all the way through today. There is one thing we need to do before we get to that, but we'll do a polynomial all the way through. Start with a polynomial and we'll get another polynomial that is its derivative. We'll start with a rational function, and then we'll end up with another function that is its derivative, and we'll start with a square root function, and we'll do battle with that. And if you can handle those 3 cases, then you can handle anything that I will give you as far as the definition of derivative goes. So when I say the definition of derivative, that's what I'm talking about. Kind of the long way. Some of you know some shortcuts. Some of you know a lot of shortcuts for finding derivatives. But when I say find by the definition of derivative, that's what we'll use. Since we're going to start with a function, take the derivative, and come up with another function, we don't always have to have it explicitly described or defined. We may have a picture. So why don't we start with that? Let's say that we have some f of x, the picture of f of x. And let's say that it looks like this. So that's what our original function looks like. And I've kind of made this a smooth function so it could very easily be a polynomial. And we'll have things that don't behave quite this nicely. And we want to kind of analyze what's going on at point A, point B, point C, and point D. Now I picked out those points, so you can probably tell me why I picked out those points. Those are the places where this function, I hope, changes direction, right? Changes from being decreasing to increasing or increasing to decreasing. And what happens when that happens on a function? If it looks like this, if it's a smooth function and we change gradually from decreasing to increasing, what happened at that exact place where that transition took place?
Negative to positive.
Okay, the slopes changed from negative to positive. What's a nice number that makes that transition from negative to positive?
0.
Right? So at these places, at A, at B, at C, and at D, whatever those x values are, the slopes of the tangent lines are 0. So if I'm going to construct a new graph, which we are, this time the y value is not the original function, it is the derivative. So I'm going to keep the scale the same. Try to anyway. So what should be true based on what we just analyzed on the original function, the f of x, the fact that the derivative, the slopes of the tangents are 0 at a, b, c, and d. What points should I plot on the derivative graph at a, b, c, and d? What should the y value be?
0.
0. Because I want to graph, now the y value is the derivative. It's the slope of the tangent. So at A, the slope is 0. At B, the slope is 0. At C, the slope is 0. And at D, the slope is 0. So I'm going to construct a new function by plotting points where they have the same x values, but now instead of the y value itself, I want the slope of the tangent line to the y value. Now the rest of this is kind of estimation. But I would pick a point over here to the left of A. It looks like the slope there is negative and fairly steep, right? So maybe the slope here is -3, making an estimate here. The slope at this point would be -3, so I'd come down here and plot -3. Maybe the slope right here is -1. And then I've plotted what's going on at A. The slope was 0. So I come up with this function. Now let's compare this much of the graph and see if the rest of our graph will do this. Everybody agree that this piece of the function right here that I'm putting a little line through, all that is decreasing, right? What should the derivative graph look like where the original graph is decreasing?
Should be below 0.
Should be below 0. Should be negative. Is that all right with everybody? So when you look at this graph and you see negative values, the fact that it's negative tells you that the original function is decreasing there. Does that make sense? Where this graph is 0 tells you that the original graph is what? Instantaneously kind of flat, right? It's just sitting there. It's not increasing nor is it decreasing. Now, as we keep going off to the right here, let's check this point between A and B. The slope is positive. I don't know what that is, +1. So let's come up here to +1. Maybe at this point the slope is a little steeper, maybe it's 2. And then what happens as I get closer to B? Doesn't it start to flatten out again and the slope gets close to 0 again? Now in this piece of the graph, and this is kind of rough here, but it's close. Where I look at the graph from A to B on the derivative function and it's positive, what's that tell me the graph of the original function must be doing there? Increasing, right? Because if the derivative is positive, that means the original function is increasing. So here's the derivative graph. It's positive. This function right here is increasing. Now tell me what's going to happen from this point. We've seen it all basically. Okay, now it's going to come underneath the axis again because these slopes are what? Negative? All of these slopes are negative. So it's going to come underneath the axis. The slopes are negative between B and C because the original function is decreasing. From C to D, what happens to the derivative graph?
Increasing.
No, to the derivative graph.
Oh, it means below.
It's
Below
above
0.
0, right? Because these slopes are all positive. So between C and D, now it gets pretty steep right in here. Maybe that's got a slope of 4. Let's bring that up a little further. And then as we get closer to D, they're closer and closer to 0 again. They're pretty nearly flat. So the derivative graph may look something like this. And then what happens beyond d for the rest of the function? Decreasing, right? So it's negative from here on out. So we do get a new function. We can even picture that function based on what the original function did. And it ought to correspond in a lot of ways. So when I check to see how the original function and the derivative kind of mesh, I first of all look for these points, the A, B, C, and D points, because that's where the original function changed direction. The slope of the tangent was 0, so I'll come down here. I know this should be at 0 at A, B, C, and D because it is the derivative graph. The next thing I check is where the original function was decreasing. My derivative graph should be negative. That works. From B to C, it's decreasing. This is negative. From D and beyond, it's decreasing. That should be negative. And in the like manner, check with where the function is increasing. From A to B, it should be positive. From C to D, it should be positive. So you can kind of make some quick checks to see how the original function and its derivative are related in that fashion. But it isn't a function. It's a completely different function. Instead of the y values being the original y values, the new y values are the slopes of the tangent lines at those points. So we want to talk about today, the title of this section is the derivative as a function. So that's one way to look at it in terms of a picture. Now, do you think if we started with the derivative of the function, could you come up with the function? Could we go the other way?
Yeah.
Okay. And actually, that's, I guess, technically probably a Calc 2 type problem. That if you have the derivative already, can you come up with the function for which it is the derivative? But basically, you do the same thing where the derivative is positive. You just make sure that the function is increasing there. And where the derivative is negative, make sure the function is decreasing. So the same way we made the parallel going from function to derivative, you can kind of reverse that process and go from derivative back to the original function.
Isn't it the integration?
Yeah, that's the antiderivative or the integral. But that's really a Calc 2 type issue. Questions on that before I move that? Okay, we're going to do 3 examples using the definition of derivative. Some of them, one of the 3, I'll actually do the one that's in the book because I want to keep it fairly simple, and the other ones we can kind of make up as we go along. But using the definition of derivative, we want to find the derivative if we're given some f of x. That is a cubic polynomial. I think that's what I want. Yes. Now keep in mind this is probably the simplest case, which is why we're starting with this case. Polynomials are nice, smooth, continuous functions. No abrupt changes in direction, no corners, no cusps, no discontinuities of any fashion. So by definition, we want the difference of the function at x plus h minus the function at x all over h as h approaches 0. So that's definition of derivative. So what is this function at x plus h? Well, whatever we're doing to x, we now do to x plus h. So x plus h, the quantity cubed, minus the quantity x plus h. That's the function at x plus h. Minus the function at x, which is the way it was handed to us. All over h as h approaches 0. Is that all right with everybody?
Mm-hmm.
Okay, what is x plus h cubed? Somebody tell me what to write down. I tell you what not to write down. It's not x cubed plus h cubed. It's not that. It has never been that and never will be that. I've seen it written that way a lot of times, but I'm still not convinced that that's what it is. Somebody want to tell me what to write down? X plus h cubed. 3 x squared h.
3 x
3
for
x h squared
H cubed.
plus h cubed. Okay. From that, we're going to subtract x, and then we'll also subtract h. And then we'll subtract everything that follows, subtract x cubed, and then subtract negative x. Okay, everybody up to that point? Anything drop out at this point?
X cubed.
X cubed
X.
minus x cubed.
X.
Okay, minus x plus x. Is that it? And that will happen all the time in a polynomial.
Equal H.
Okay, and everything else, this will also happen every time in a polynomial when we're using the definition of derivative. Everything that's left in the numerator should have an h. So we'll factor that out. Don't forget that when you factor an h out of negative h, that leaves negative 1. So you should be able to redistribute that and be back to the previous step. Is it okay to reduce h over h? That'd be nice. Is that legal?
Yep.
That's legal as long as h is not 0. It's not 0, but it's approaching 0. What terms remain, or tell me what terms disappear as h is allowed to approach 0? Okay, the ones with h disappear, right? As h approaches 0, this term approaches 0, this term approaches 0, and we're left with everything else. So our answer is a function in terms of x. And some of you know the shortcut. We know a whole lot quicker way of getting there. Thankfully, when we get to that point, we'll all rejoice together. But right now, we're kind of mired in this definition. It serves a purpose. But if this is the original function, then the derivative is also a function. And keep in mind what it is. It's not changing now. It still is the slope of the tangent line. So if you want to find the slope of the tangent line to a curve, to this curve, x cubed minus x, what do you do to find the slope at any point? Plug in the x value. What do you do to it? You square it, triple the result, subtract 1, right? That's how you find the slope of the tangent. So it's a slope. It's a variable slope. So as x varies, so does the slope vary. But it is also a function. Now, if we were to graph, and I think we ought to at least make a sketch, and if we were to sketch x cubed minus x, and we were also to sketch 3x squared minus 1, we ought to have the same relationship that we had on that first original picture and slope of the tangent picture that we had up here before we did this problem. Let's see if we can do that. So if questions on this before it gets moved? Think you'll have an opportunity to show me at some point in time that you know how to do this with a polynomial? And they all collectively said yes. Okay, that will be certainly a question that you will see. Definition of derivative with a polynomial. So our original function was that, and our derived function, our derivative function, was that. Somebody sketch on your graphing calculator x cubed minus x. That's an odd function, right? Gosh, we're supposed to be able to forget about that. That was on the last test. It's an odd function, which means there's symmetry with respect to the origin. At 0, it is 0. At what, 1, it's 0. And at -1, it's also 0. Is that right?
Yeah.
What's it look like from 0 to 1?
Negative.
Go down?
It's decreasing.
Decreasing
Increasing.
and then increasing? Does that?
Yeah.
Is that right?
Yeah.
And what's it do over here?
Opposite.
Opposite, right, because it's an odd function. So that's not a real unbelievably accurate method of graphing, but that's the shape of this graph. Now, let's pretend that we don't know what the derivative looks like. We know that to be a what? Parabola, right? 1 unit down. Well, I'm not pretending very well, am I? It's a parabola 1 unit down that is fairly skinny and opens up, right? Now, let's see if we can get that. What do we want to pay attention to? Where the derivative on this one is 0. Okay, well, for us right now, we're just kind of making a rough sketch. That's somewhere between 0 and 1, right? Everybody agree that the slope of the tangent is 0 right here, whatever that is. And the slope of the tangent is 0 right here, whatever that is, some value between 0 and 1. Everybody all right that I plotted? This is the original graph. This is the derivative graph. Okay, where the original function is increasing, that's increasing, right? What should my derivative function be?
Decrease.
Positive, right? Where the original function is increasing, the derivative graph should be positive. Okay, here's where the original function is decreasing. What should my graph be?
Negative.
Negative. Is that all right? And here the original graph is increasing. My derivative graph should be positive, right? Is that what it should look like, according to what we already know to be true about the derivative function? Yeah, we know what 3x squared minus 1 looks like. It's a parabola, down 1 unit that opens up. So those things that we saw to be true in our first original function derivative graph are in fact exhibited here as well. So it is a function. We can track from the original function to the derivative, or hopefully we can track from the derivative to the original function. Questions about that one? We don't have to do that on every problem, but that's pretty easy to do on this problem, is to sketch the original and sketch the derivative. Suppose I wanted to know, I said it's somewhere between -1 and 0. Suppose I wanted to know where that was. Do we have the ammunition up here to find out where that is, where the derivative is 0?
Plug in 0 for x.
Not plug in 0 for x, but
Oh, for the prime x.
right, for the f prime of x. So if we want to know where the derivative is 0, then we know what the derivative is. It's 3x squared minus 1, so we'll find out where it is 0. So positive or negative, either the square root of 1/3, you can leave it like that, it's not a problem, or the square root of 3 divided by 3, 0.577. Does that sound right? Somebody punch in the square root of 3 divided by 3.
Yeah.
Is that right?
Mm-hmm.
That's a sad commentary on my life to know that I would know what the square root of 3 divided by 3 is off the top of my head. So that, we said between -1 and 0, that's negative 0.577. And this one is positive 0.577. That's where the derivative is 0, and in fact, that's this point right here, right? That's the x value we throw into the derivative that makes it 0. So that's a point on this derivative graph. Those are the two x-intercepts on the derivative graph. Okay, that's belaboring that one enough. Let's go on to the next one. Let's say that our function is the square root of, I'll just make this one up. Let me see the one that's in the book. In the book they have the square root of x, so let's just go 2 square root of x plus 1. There's our function. We want to find f prime using the definition of derivative. All right, so we're going to do this long-winded limit thing again. What's the first thing? Let me just go ahead and write this down. Isn't it the function at x plus h minus the function at x all over h as h approaches 0? What is this function at x plus h?
Go to 2x plus h.
Okay, just do whatever we did to x, we now do it to x plus h. So we'll double x plus h and add 1. Don't make that any more complicated than it is, right? Whatever you were doing to x, you now do to x plus h, the quantity x plus h. From that, we'll subtract the function at x. All over h as h approaches 0. Does that look right? Definition of derivative? This isn't absolutely necessary, but we could distribute that. Now here's a process that you probably used in algebra. Somewhat similar. You rationalized the denominator in algebra. Algebra 1, algebra 2, you made the denominator a rational number. Got rid of radicals in the denominator. Remember how you did that? Multiplied by the conjugate, okay, of the denominator. So you've done this process before. Now we look at the numerator, and we're going to multiply by the conjugate of the numerator. Which is the same two radicals. Different SIGN in the middle. Multiply the top by that. And the bottom by that. Now that might temporarily make this problem worse. But I think in the long run it's our only option for eventually getting rid of the potential for having 0 over 0. What is that radical, that ugly radical expression over itself? What is anything over itself?
1.
1. So we multiplied by 1. That's clearly legal. All right. How does that help the cause in the numerator?
It's going to be able to cancel out, right?
Doesn't take
There's no
the
middle term when you multiply those two, right? When you have a plus b, and then you multiply by a minus b, what do you get?
a squared, b squared.
A squared minus b squared, right? So that's the same principle we're looking at here. We've got something minus something, a minus b. We're going to multiply it by a plus b, so we ought to get the first thing squared. This is, you won't write this down, probably, but I'll write it down since it's our first example. The first term squared minus the second term squared. And in the bottom we've got this mess. So it helped the numerator. Didn't do anything to help the denominator. In fact, we got some extra baggage in the denominator. So what is any square root squared?
Itself.
What's under the radical, right? So this square root squared is 2x plus 2h plus 1. This square root squared is 2x plus 1. About all right with that? Let's see if we can, without distributing this, are we going to drop any terms out of the numerator?
2x and 1.
Okay, we're going to have 2x minus 2x, right? That's going to be gone.
1 minus
We've got 1 minus 1. That's going to be gone.
You can get rid of the H.
And then we also have, I think I probably ought to write down another step for this rather than have too much of this going on in the same step. But the nice thing is now we've got h over h, right? H is a factor of the top. H is clearly a factor of the bottom. So in the numerator we've got 2h. That helped. So h reduces, as long as h is not 0, which it isn't exactly 0. Now is it okay, since we got rid of h in the numerator and h in the denominator as a factor, is it okay to let h be practically 0?
Yeah.
Yeah. And h, as it diminishes to practically 0, does away with that term right there. So 2h, as h approaches 0, 2h approaches 0. So that is what? We're still left with the 2x plus 1. And over here we still have 2x plus 1. What is anything added to itself?
2.
2 of that thing. So we've got the square root of 2x plus 1 plus another square root of 2x plus 1. So in the bottom we have 2 square root of 2x plus 1s. The 2's reduce. So that was kind of messy, right? But the important thing there is to remember to multiply by the conjugate of the numerator, and that helps things. Yes, Tiffany?
With the denominator, why did you add them instead of multiplying them?
They were added all along. So when we were up here, this term right here shows the sum of those two terms, and it stayed the sum all the way down. So the only thing is, after I let h approach 0, this term disappeared, but that doesn't change what we were doing to them. We're still adding. Now the only thing that was being multiplied in the denominator was h. H was times this, and then we ended up with an h in the top, so the h over the h, they reduced. So there's the multiplication. The rest of it was addition.
On a test, could we leave the square root in the denominator?
Yes.
All right.
Yeah, not an issue.
Okay.
So what we have here is a new function. It's a function in terms of x, just as our original function was a function in terms of x. That tells us what the derivative is. Now we're not going to graph the original function here, but let's at least do this much before we leave it. The original function, yeah, I'm going to take this off. Is there any issue on anything here before I go beyond? Okay. Let's take our original function. And our derived function. And there is an example similar to this in your book, but it'll give you a look at something that's a little bit different than that. we know this to be a half of a parabola, right? If we just graphed y equals square root of x, it would look like this, right? What happens now, and this is also a half of a parabola, this function. It's positioned a little differently in the plane, but it's a half of a parabola. What happens on a half of a parabola as you go further and further out here to the right? What happens to the tangent lines?
Slope approaches zero.
Yeah, don't they get flatter as you go out to the right? Which also is true, they approach zero. Now, does that happen here? As we keep putting in larger and larger values into the derivative function, do we keep getting values that are smaller and smaller and smaller? We do, right? And as we put in tremendously large numbers for x, doesn't that fraction that I circled approach zero? Right? So it seems like they could be paired up together, one as the derivative of the other. So if this is the original function, it seems like, it makes sense anyway, that 1 over square root of 2x plus 1 could very easily be its derivative. Because that's what happens when you go out to the right. The slopes get smaller and smaller and smaller and eventually approach zero. So if you want to look at that graphical comparison, graph this one on your graphing calculator, not now necessarily, and graph that one and see if you get that same graphical matchup that we've had on the first two that we've looked at. The third one, we want to start with a rational function. I don't know, just make one up, about 2x minus 3 over 5x plus 4. Good old rational function, the quotient of two polynomials.
What is it with the square root? I don't know. Just remember how to do it.
Okay? So if you notice, every first step on these three problems is the same, which is just a restatement of the definition of derivative. Okay, tell me what to write down. What is this function at x plus h?
2 times x plus h minus 3.
Over?
5 times
5
x plus 8.
times
X
x plus
plus
h
h.
plus 4.
Okay, everywhere there's an x, put in an x plus h. That's right. There's the function at x plus h, Tiffany.
Would using the other definition be easier on this one?
Function at x minus the function at a,
All over x minus a.
all
Yeah.
over x minus a. Trying to look ahead. I think it's about the same amount of work. Because on that one, you'll also have to get a common denominator, which is what makes this one kind of cumbersome as well. So you're kind of stuck with having to get common denominators.
Okay.
Because you're trying to subtract two fractions. My guess is they're about the same amount of work. So the function at x plus h minus the function at x, well, the function at x is the way it was handed to us. All over h as h approaches 0. Now that's nothing more than a kind of an ugly algebra problem. That's all that is. At this point, I mean, you got to know the definition. There's a certain amount of memory here to this, memory work, but most of this problem is algebra. So it looks like the common denominator is their product, right? The product of these two denominators. Let's do this. It's not absolutely necessary. So let's multiply the first fraction by 5x plus 4 over itself. And the second fraction, let's multiply by 5x plus 5h plus 4 over itself. That's legal, right? Multiplied each fraction by 1. A different version of 1, but by 1. Now the purpose of that was to get a common denominator. So I'm just working in the numerator now. In the numerator, we have this. That's the common denominator, right? And I've got two ugly pieces in the numerator that will stay in the numerator of that combination of fractions. So that's just the numerator. I've combined the two fractions into a single fraction, which we have some simplifying to do, which we'll do in a minute. Now, all of that is divided by h. How can I accomplish that same thing? Okay, let's multiply by 1 over h. So we don't want complex fractions if we can help it. So all this that I'm framing, that was the numerator. And then the h in the denominator has now been, instead of dividing by h, we're multiplying by 1 over h. All right, let's see what we get in the numerator here. We have, let's distribute this 5x to all three of these pieces. Tell me what to write down. 10x squared plus 10xh minus 15x. Is that right? Yes. Okay, now let's distribute the 4 to all three of these pieces. 8x plus 8h minus 12. Everybody all right with that? Algebra, right? I mean, this isn't calculus, but it's helping us get to a calculus answer. Just to keep track of my signs, I'm going to go ahead and just keep that minus sign here and then subtract everything that follows later. So let's distribute the 2x to these pieces. What do we get?
10x squared plus 10xh plus 8x minus 15x.
Okay, wait a minute.
8x minus 15x.
Minus 3 now is going to get sent to all three of these.
15h minus 12.
Minus 12. Everybody all right with all that?
Yep.
We get agreement on all that. In a class this size, we're doing really well.
Many numbers.
Can we get rid of some terms before I distribute the negative through all that second bunch?
Yeah.
Let's try it. Looks like we've got a 10x squared minus a 10x squared, right? That's gone. What else?
10xh.
10xh minus 10xh.
8x.
Okay. 8x minus 8x.
15x.
12.
Minus 15x plus 15x, right? That's going to be minus a negative, which is plus.
12.
Minus 12 minus a negative 12 is plus 12. That helped, right? Kind of helped the cause quite a bit. All right, what are we left with in the numerator?
23H.
Looks like we've got an 8H minus a negative 15H, which is 23H. The nice thing about that is that H is a factor of the numerator. And as long as H is not 0, those can reduce. That's kind of why we did all that algebraic mess anyway, is to get beyond that step. So I was talking to a sports writer last night at State's basketball game, and he said, yeah, I've been watching you on TV. He said, I can get you with the X's, but when you start putting those Y's in there too, he said, you lost me then. So I imagine he is really struggling with the H's at this point in time. Sorry about that, AJ. What happens now? It's legal to make H approach 0. So this term, 5H, disappears on us. And tell me what the bottom is. Okay, we got 5x plus 4 times another term, which is also 5x plus 4. So that's 5x plus 4 squared. Do not have to simplify that any further, because what would we be doing with this? We would be plugging in an x value, and there's nothing to be gained. In fact, probably a little bit to be lost by having distributed that, because then we've got more places to put our x value, right? Right now we've just got one place. Plug in 2 for x, and due to x, or due to 2, what's been done to x, and we're in business. So what did we start with? We started with a rational function. We ended up with another rational function, a different rational function, which was the derivative function. And again, if you want to do that same picture process, isn't that what we got? 23 over 5x plus 4, the quantity squared. Yes, that's right.
What's that 1 over H? Got multiplying, is that?
Well, we lost that. This 1 over H, that came from this division by H. Division by H is the same thing as multiplying by 1 over H, and that kept us from having a fraction within a fraction. But we lost that down here with this H over H. So that eventually worked out nicely that we were able to reduce H over H. Tiffany.
I did the other way. I got a different numerator.
You did?
Yeah.
Okay. Well, maybe we made an arithmetic mistake. Notice I said we, because nobody caught it as I wrote it down. So we make arithmetic mistakes. Let's see. I know the denominator's right, using the shortcut. What'd you get, Tiffany?
I got an 8.
An 8 in the numerator?
Is this a cushion rule?
Just pretend that you didn't see me writing this down.
Okay.
There it is. Right? 23?
Oh.
That right?
When are we gonna hand that? Yeah.
So we did get it right. And it's kind of a long process. We're not stuck in this process forever and ever. We will get some shortcuts. Let's see if there's anything else that we can... Yeah, I think I can probably do this much, and then we'll be able to start fresh with things that are not differentiable tomorrow. There are lots of notations. Seemed like everybody that came along in mathematics over the years kind of put their own little stamp on calculus. So there's lots of notations for derivative. We've already seen several. We've certainly seen these, f prime and y prime. We could have the derivative of y with respect to x. That's a common notation for derivative. The derivative of the function with respect to x. The derivative of f of x with respect to x. All these are the same thing. They're all derivatives. You could have derivative with respect to x of y, derivative with respect to x of f of x. All the same thing. So if you see any question that has any of these in it, they're asking you for the derivative. Now we've also used this to mean that that's the derivative at a certain x value. If you happen to use this notation, it takes on a little different look. You have to write it. It's a little more cumbersome. That's why this notation and this notation are so nice, is that you can just relate it to the original function. If the original function is f, then our new function is f prime. And then if you have to plug in a value, it's just the f prime at that value. But those are different kinds of notation. And we'll have some other types of notation for second derivative, but it's still all second derivative. Let me get you started with some of the problems from this section. And by now, we're not done with it. In fact, we're just about halfway done with this section. So this is from 2.8, page 167. Let's see, these are, I guess, the ones that we could be ready for. And 3 more. Okay, and there will be a couple of other problems, not many, but some other problems based on what we cover tomorrow. So that finishes day 21.
Is this due tomorrow?
No. But the following day, yes.